Now, this story starts with a collaboration with Jane Irrigation, one of the biggest micro-irrigation firms in the world. And Jane came to us and said, we're a company that deals with water. Most of our clients are poor, rural people that don't have access to clean drinking water. We should be able to do something about it, but what do we do? And the reason I put this picture up is this is what data collection looks like in my group a lot of times. There's me on the left, my graduate student on the right, one of Jane's engineers in the middle, and a bunch of rural farmers telling us what they need for clean water. And I think another important point of this story is that when we started this, we didn't jump in and say, we're going to make a desalination system or we're going to make a water filter. We took a step back and used a blank slate and said, what is the market telling us that we need for water purification in this space? And as we dug into the market in India, we found that salt is by far the most prevalent contaminant. In the picture on the left, anywhere where you see a color other than blue, you have groundwater that's salty enough to taste. And that forces people to often drink other sources of water, which can make them sick. Also, the water you have available in India is pretty stressed. And the plot on the right shows how stressed it is throughout the country. Now, not all as bad, though, is that where you have the most stressed water and the most salty water, you also have the most sun energy. So we started putting together a detective case of what this was telling us. And given the prevalence of salt and how stressed the water was, this showed us that desalination is probably the highest impact solution we could bring to the table, and that we want to utilize the water available as effectively as possible, so we want to minimize waste. So that gave us some of the socioeconomic side of the problem, but as engineers, we also had to look at the technical side. And if you look at the median village size throughout India, it's 2,000 to 5,000 people. That accounts for a quarter of the population, and most of those people don't have grid access to electricity. So you look at that water production, lack of grid access, that points you to photovoltaic power as a power source. At this point, we had to decide what sort of technology would be most appropriate to get the salt out. Well, the industry standard is reverse osmosis. I'm sure most of you have heard of this. And the way it works is you apply a mechanical pressure, input energy, and force water through an osmotic membrane. So you separate the salt on the high salinity side, and you produce your desalinated water on the low salinity side. Well, we found that there's another technology used less often called electrodialysis. It's mostly used in industrial applications. But the way this works is you flow water through ion exchange membranes that can pass either positive or negative ions of the salt ions. On either side of those are electrodes, which you can apply a voltage with. And as you flow the water down through, when you apply that voltage and flow energy through the system, it sucks the positive and negative ions in different directions, and you end up with channels of diluate, which is your desalinated water, and concentrate, which is your salty water. Now, why this is important from an energetic perspective is that both of these technologies depend how much energy they need on how saline the water is. So if we look at how saline the water is in India, which is usually around 1,500 to 2,000 parts per million, electrodialysis requires half the energy as reverse osmosis. This then cuts the capital cost in half of the off-grid power system that has to run this thing. Furthermore, you compare RO to ED in this space, electrodialysis wastes only 5% of the water, whereas RO, you typically waste about 60% of the water. So you actually need double the water to feed into your system. So we put all of this together into this big socioeconomic and technical detective case, and that pointed us to photovoltaic-powered electrodialysis as a potentially disruptive solution for India. Now at this point, it serendipitously coincided with USAID's Desal Prize, which we built our first full-scale desal system and ended up winning that prize. And that caught the attention of TATA Projects, a big infrastructure company that is making village-scale RO systems but can't engage the market off the grid with RO, but they can with ED, and they're funding us now. Also caught the attention of UNICEF, which said, hey, this could work really well in the Middle East. Let's pilot in Gaza. And we're doing that this year. Additionally, we're doing 2 pilots in India sponsored through USAID, and this is a picture of one with our partner Jane Irrigation at their factory in India. So to wrap up, I think what's so important about this work is the partnership in this socioeconomic and technical detective case we had to do. Because what that showed us is that electrodialysis could impact people like rural people living in India. It also could impact people in places like Gaza. We're seeing with TATA projects, we could also make small-scale municipal systems to go on top of apartment buildings to desalinate water. We're also working on home-use electrodialysis systems that can cut water wastage to 5% rather than 80% for RO systems. And because we're diving into the physics and the engineering behind this problem, we're seeing how we could make lightweight, no battery systems which could be deployed for disaster response or military applications. So we wouldn't have seen this whole space had we not done this socioeconomic and technical detective work. And because we did it, we saw that electrodialysis desalination can impact people of many different demographics from around the world. Thank you very much.